Hello, everybody. Welcome again, because I see quite a few faces that I've seen before at our talk series. Again, this is a series of talks and scientific communications co-hosted by the CyberCenter and by Brian Lamb School of Communication, dedicated to this broad, very generous topic called computational social science. Some of the things we're talking about here deal with big data, and that's probably what computational social science communicates to you, but we take it to be much broader than that. And it might include things as exotic as automated content analysis. I'm Sorin Matei. I'm an associate professor in the Brown Lamb School of Communication. I'm the scientific director for computational social science at the CyberCenter. I work very closely with my colleague from computer science, Elisa Bertino, the head of the CyberCenter. Unfortunately, she has a family emergency today. She cannot be with us, but she's greeting you all, and she's extending a welcome to our guest today. Our guest is Professor Ming Ming Chiu, who is one of those rare birds we are so happy to have here with you. He is a truly interdisciplinary scholar. He is the Charles Hicks Professor of Educational Psychology and Research Methodology in the School of Education, and he covers quite a bit of ground. I'm looking at my notes here because I don't know them all by heart. In terms of intellectual pedigree, he got his BS in computer science, so he is at home in this building and is part of the campus at Columbia University. Then he got an educational, a master in education at Harvard University in interactive technology. At the time, I will not say the year, because you don't want anybody to think anything about the time, but at the time when interactive technology wasn't exactly what we have today. So he is an early adopter and pioneer of bringing interactive technologies to education. And finally, he got his PhD in mathematics education at UC Berkeley. Now, Professor Chiu studies classroom conversations and inequality mechanisms with advanced statistics. As a research methodologist on the one hand, advanced research methodologist on the one hand, and then as an educational research scholar on the other hand. He's especially interested in how teachers and classmates' social metacognitive processes affect classroom conversations, and to analyze these conversations, but not only for this purpose, because as you will see, this can be applied to a variety of disciplines. He invented it, an efficient statistical discourse analysis method. In addition, he studies inequality mechanisms that reduce the learning of both rich and poor students. Professor Chiu has a distinguished research career. He's published tens of articles, and he has been very active in fundraising, and he has a broad experience in this field. And in our conversation, we want to ask for his opinion or mentoring advice, please do so. Without further ado, I give you Professor Chiu. Thank you so much for joining us.
So thank you for joining me on this talk today. Can you all hear me? Okay. So I want to talk about automatic statistical discourse analysis of online message sequences. And I'd like to thank my research assistant, Troy Ting, who's been very helpful in helping write and test the computer programs. So in general, there are many problems that's very difficult for one person to solve, but can be done when groups of people work together. So here's an example of this. Design an online science lesson that tests hypotheses from Western and Chinese zodiacs. So in order to do this problem, one person would have to have great understanding of teaching, of science, of technology, astrology, and also Chinese culture, which is very hard to find one person. But you can have groups of people with varying amounts of knowledge of these different aspects work together and create a pretty good lesson. And this is indeed an example of the problems that the participants in this study used. So in general, we want to look beyond simply assessing online discussions as outcomes. We don't think about only outcomes, but also processes that help create them. And so in particular, we want to think about students' thinking processes while they're working together. And so the question I'm going to look at today is, how do classmates' actions affect one student's thinking? And if we understand the process of how students work together, that can help us teach online much more effectively. So problems like the one I showed you earlier are often very difficult. And so when people are working as problems, they try to think of new ideas. They ask each other, like, how's it work? How's it make sense? To try to explain what's going on. They try to summarize what they understand to put into a coherent solution. So it's not surprising that when groups exhibit more of these beneficial processes, they're much more likely to solve a problem. So a natural follow-up question is, what sequences of group actions tend to increase the likelihood of these beneficial processes? So the theoretical framework that I helped develop is called social metacognition. So I think many of you are familiar with metacognition, which is how people monitor and control one's own knowledge and actions. They think about, how much do I understand of this? Does this proposal to solve this problem make sense? Why would it work? Why would it actually solve the problem? They think about, is the answer correct or not? If it's not correct, what's wrong with it? So we can take these individual metacognitive acts and look at the corollary of them, which is social metacognition. Instead of looking at an individual, we look at a group. So social metacognition are group members monitoring control of one another's knowledge and actions. And so these are the same sort of actions that individuals take, but done within a group context. Questions, commands, evaluations. And this is very important because most individuals have very poor metacognition. It's hard for individual people to do this by themselves. And group is much easier to divide the efforts of each person. So one person might be thinking about how to solve a problem. Another person can think about how to evaluate. And by dividing the tasks and the efforts, it's easier for the group to coordinate. So it's possible that social metacognition can improve individual cognition over time. So I'm going to look very microscopically at particular messages in online discussion. And the key question we're asking is, how do previous messages, earlier messages, affect the next message? So one outcome that I want to look at is a new idea. What affects the likelihood of a new idea? And so it might be affected by previous classmates' opinions. So we'd expect that if someone gives an opinion that's kind of rough, it's not very clear, that might help other classmates, groupmates, create a new idea. So we expect these two instances to be positively correlated. We can ask many more questions about how cognition affects new ideas. So examples affect an idea, elaborations, other new ideas, explanations. And so to give you a quick sense of the results, the solid processes indicate significant effects. So opinions do indeed affect the likelihood of a new idea. Examples, elaborations of new ideas do not. And we wouldn't really expect explanations to, but you'll see lines in the slide there. Social metacognition also affects the likelihood of a new idea. When someone asks about how to use an idea, it often sparks an idea that's slightly different from the original idea. But asking explanations of different things tend not to increase the likelihood of subsequent idea. I'm going to look at multiple outcomes in the same model. So also asking for explanations. It turns out none of the cognitive elements improve a lot of likelihood of asking for explanation. But social metacognition does. Essentially, questions tend to foster more questions. Questions about using an idea, questions about how the idea makes sense, tend to lead to more questions involving explanations. I'm also going to look at what predicts actual explanations. So it turns out lots of cognitive elements do predict explanations. Opinions, examples, elaborations make it more likely that someone's going to give an explanation. And likewise, asking about use, asking explanations, and offering a different opinion tends to lead to more explanations. And lastly, summaries. It turns out that generation of new ideas tends to be summaries of those ideas. And actually, it turns out that if you have a greater likelihood of any of these above elements, they tend to contribute over time to foster summaries. So for our data, this is actually a relatively small data set. It's only one university course, 17 students over 13 weeks. Course is education technology, and they use an online discussion. And so over 13 weeks, they discuss a problem that a teacher poses every single week. There's a requirement that every single student has to post at least one message per week. And as it turns out, they generate way more than that. Over this course, there are 1,330 messages, which comes out to 100 messages per week, and about 6 messages per student. So they do much more than they had to. And as you can see, if you have 100 messages a week for just one course, this is really hard for a teacher to go through all of it. So there's a great need for some sort of tool to help teachers go through these messages. So a little more about the context. This environment is a little bit different from most online environments. Here, the teacher created cues. So you can click on these cues and type your message. And cues are basically 4 types. I have a new idea. I want to elaborate someone else's idea. I have an explanation for something. And I'm going to summarize. So students can click on these cues and write the notes, or they just ignore them. And actually, in over half of the cases, they didn't use cues. And so these are examples of cues. In addition to that, students also create their own cues. The teacher let them create things that they thought they would be useful. And in fact, they created 5 of them, and these were used a lot. In fact, they used the student cues a lot more than teacher cues. They were, I have an opinion, which is different from my idea, which is less formal. I have a different opinion, an example. I want to know how this is used. I want someone to explain this to me. So this is very important because it helps us with validity issues. Often when you have just data and you're imposing your own framework on it, the common question is, well, do the participants actually think this way? And here we see that by using cues that students create themselves and looking at the students whether they choose to use cues or not, this gives a sense of how valid they feel these cues are. This then informs our external observability perspective, going from emic to edic. And here, when we write computer programs to classify these different messages, we're starting from a base where students already believe this, and we know that they find this valid. So this allows us to write computer programs for large data sets for students don't necessarily self-coding messages. So how do we analyze these sequences of group processes? The first thing to do are case studies. You don't need to have a particular method. You look at it carefully. You see what relationships are going on. The next step is to count instances of certain types of events, say new ideas. You count how often those occur. And then you look at the probabilities. How does the probability of, say, a new idea increase or decrease if there's a question given before that? And so when you combine statistical tests, we have something called sequential analysis. And sequential analysis is very good for very simple models, like does a question precede a new idea. But it's also good for things that are more complicated. For instance, is this relationship true for every single group? Is it true for the beginning versus the end of a problem-solving session? And so for that, we need more complex statistical methods. And so, quite a long time ago, I was doing my PhD dissertation. And so I had this idea, we can use statistics to analyze conversations. And so naturally, I talked to the statistics professors at my school. I asked them, so how can I do this? So I thought about it for a while. And they basically came up with, you know, man, you should probably do a qualitative dissertation for now. Because, there's really no way of doing this. So over the next 10 years, I talked to a lot more statistics professors. I read a couple of statistics books. I developed something I call statistical discourse analysis, which solves a lot of different problems. And so I'm going to go through them today. So there's a whole bunch of analytic difficulties. The first of which is, how do you model earlier messages affecting later messages? So when someone says something like, Anna says y 0.1, that might be affected by who Anna is. She's female, she's very smart, she's got really good grades in mathematics and other courses. It also is affected by her setting. Who or her groupmates that are working together with her? Are they male, female, different racial backgrounds, ethnicities? How well they did in this course before or earlier courses? What's the classroom context? How does a teacher? How does a school? How integrated is the program? So you have different layers of characteristics that might affect what a person says. On top of all these variables, we can also look at the previous person affected what she said. So in the previous message, what are those characteristics that might affect what Anna says? And we go back further in time. Oops. 2 messages ago, 3 messages ago, 3 messages, 4 messages ago, so on and so forth. So you get a very complex model of what's affecting likelihood someone's going to say something. For example, you continue like that. So the way we model that is something called vector order regression. And this is taken from econometrics, where they look at what happens in earlier years, earlier seasons, how they affect what happens later. So you can look at things that are not just immediate, which immediately happen, but you also go further back in time. So that's one problem. A second analytic difficulty is a tree structure of node sequences or message sequences. In a face-to-face conversation, things are typically a standard sequence. But on an online forum, you typically have branches where people evolve in different directions. So think about something like this. The first topic message on the far left might be the initial question. And the first person responds to that. The second person responds to the first reply. But then the third one responds to the initial message. So you have different branches all of the same topic. In a face-to-face conversation, so the way we deal is we're store the information. And then we're going to use that information as a variable to track what happened earlier. So in face-to-face conversation, you typically one follows the other. Here, in the first term, Anna says, do 3 times 4. The code we're going to use for this is a new topic, which is indicated by asterisk. There's no previous term. So let's look at the second term. In response to Anna, says 3 times 4 equals 7. He's agreeing with what Anna said. We should indeed do 3 times 4. The previous term is the first term. So what we're going to do is we're going to store that information in a different variable. So we store the asterisk indicating the topic in a different variable. And we do the same thing for all subsequent terms. Eva says, no, it's 12. She disagrees with that. So that's a separate code. The previous term is 2, so we store the code from term 2. So we can apply this to online instructions as well. So the first message is the same, pretty much the same. So the database looks pretty much the same. The difference now is that instead of Eva responding directly to Ben, Eva responds to Anna. So here's the difference. Instead of the previous post being 2, it's 1. So we store information from first term, which is the asterisk. Does that make sense, everyone? So basically, we're just storing information to indicate what the previous message is. Once we have the previous message, we can rebuild the tree structure. And the analysis is going to go backwards, just follow what the previous messages were. So by storing the information, we're able to do analysis. Another issue is like when people have different topics of conversation, those discussions can be very different from each other. So we want to be able to model that as well. And so a standard way of doing this is multi-level analysis, also known as hierarchical linear modeling. So the lowest level analysis is going to be characteristics of each message. Above that are going to be topics of conversation. So you have some topics that have certain messages, or topics that have other messages. And you allow the message relationships to differ across conversations. Another issue is time periods. At the beginning of the discussion, it might be really different. You might really know what's going on. Towards the end, you might have a much clearer idea. You'll be much more likely to create new ideas. So we want to be able to model time periods as well. And to do that, we use something called breakpoint analysis and a combination of multi-level analysis. So when you have like a whole long discussion, there could be critical events that radically change what happened before to what happens afterwards. So someone might have a great idea that helps people understand how wrong. Someone might get really upset and insult someone else. That might really tear down discussion. So there are critical events that really radically change interactions. And one of the contributions of statistical discourse analysis, we can statistically identify them, rather than rely on human subjective judgment. So what we do is we have a computer program where you have, let's say this is your discussion, and which basically tests every single possible message in that discussion. So we create a computer program that will create these models. Each model basically tests at this particular potential breakpoint. Because what happens before different from what happens afterwards. And so you're going to have, for one breakpoint, let's say you have 200 messages, you basically have 198 possible breakpoints. But there might be multiple breakpoints. You might have 2 breakpoints. Then you have to test every pair. For 3, you have to test every triple. And so you can see the combinatorial explosion. It's basically an n by n by n problem. It's an n² problem or n³ problem, n to 4 power problem. So it gets really huge very quickly. So practically with the standard computer, desktop computer, you can't really test more than like 7 or 8 breakpoints. We actually have mathematical tricks that reduce time it takes to solve these problems. So we can get up to about 10 breakpoints. And you have supercomputers, you can do a lot more. But effectively, 10 breakpoints is probably more than what you need in most conversations based on what I've seen so far. So you have all these different models, all these different regression models. How do you find the best model? Well, it turns out that Bayesian information criterion is a good way of testing this. It's much better than all the other information criterion we can use because it's unbiased and it'll give you a consistent answer regardless of how many data points you have. So you find the model with the smallest Bayesian information criterion. That'll tell you which set of breakpoints will explain the most variance. The fewest number of breakpoints accounts for most of the differences across time. So here's an example of one group. We use for every single group, every single session. And here you see at the very beginning, they have lots of new ideas. They're doing great. And then at the first point here, someone starts talking about their summer vacation. And then they're basically not looking at the problem for a while. Someone throws a few ideas. Then they realize they have to get back to the problem. They have more new ideas. Then they have a calculation that's wrong. And it leads them off in a totally wrong direction. So there are lots of wrong ideas when you're on there. And then someone figures out the errors. And then they can solve the problem after that. So here you see there's 1, 2, 3, 4 breakpoints that divide the problem-solving session into 5 different time periods. 1, 2, 3, 4, 5. So now that we have these time periods, we add them to our multi-level analysis. So we have now each term talk is the lowest level, each time period is the second level, and then each discussion is the third level. And you can go higher than that, groups, classrooms, so on and so forth. So another problem we have is serial correlation. When there are messages that are really close to each other are probably a lot more similar than messages that are really far apart from each other. And so we don't model this properly, you get bias in the results. So what we do is we use Q statistics to test whether or not there is indeed serial correlation. If there is serial correlation, we model it. So often we can do this, predicting a new idea. New ideas are probably related to the likelihood of the new idea in the previous term. So if you add a new idea in the previous term, that'll often help take care of your serial correlation. So if there's a problem, you try to model it. So these are major issues that we face. There are also more mundane issues. For instance, we often have discrete outcomes. Is there a new idea, or is there not a new idea in the term talk? So logic probe is a standard way of dealing with this. Also, in my model, I have multiple outcomes. So we use a multivariate outcome model. So these are often systems equations or structural equation models where you have multiple outcomes and multiple relationships between the explanatory model and these outcomes. Another problem is that the data I'm looking at, a lot of things don't happen very often. So for instance, students often have new ideas, but they rarely have summaries. They really summarize what they're doing. Explanations are relatively rare. So all these things occur less than 25% of the time. If we don't model this properly, we'll get bias in our results because they're skewed toward, especially very low percentages like 10% or 5%. You can get bias in the results. So, fortunately, we can compute exactly what that bias is. And then we just subtract it from our regression coefficients. That'll create unbiased estimates. There are also explanatory model issues, the remediation effects. So it might be that a question doesn't cause an idea directly. It might cause an opinion, which then causes an idea. So we model the remediation effects, and we use something called multi-level remediation tests. If you use a standard remediation test, it doesn't take account of different levels of structure, and so you're not going to get good results. There's also an issue of false positives. When you don't have just 1 or 2 hypotheses, we actually have something around 20 hypotheses. And when you have a lot of hypotheses, the chances are that you get a single result is much higher. So let's say your p is 0.05. 1 out of 20 times, you're going to have a significant result, even though actually not. So when you reduce the likelihood of positive bias, false positives, by using this two-stage linear step-up procedure, which is basically a simple algorithm where you recompute repeat values. There's also issue of missing data. This is often the case in conversations and in online discussions. Sometimes you have this problem, data gets lost, or people don't enter data properly. So we estimate the missing data using something called Markov chain multiple imputation. There are also other ways of doing it. You can also use full information maximum likelihood. This way you have a complete data set. And this is much better than simply dropping certain messages that are missing variables or missing cryptographic information. And lastly, we want to see if our results are robust. So we test separate outcome models. For instance, we only test one model UI first. But those results similar to the results we get when we have all 4 outcome variables. And we also test data subsets, so for particular groups, particular classes. And we also test the original unestimated data. So all these results should be consistent with results robust. So now let's look at our results. We have 4 outcome variables. What affects like the new idea, asking for explanation, an explanation, or summary. That's affected by individual variables, for instance, gender. Men are much more likely to give explanations than women. On the other hand, men are far less likely to ask for explanations compared to women. And so, black lines indicate positive effects, red lines indicate negative effects. And thicker lines indicate larger effects. It also turns out technology is related to people's interactions. So people with very good technology, they're far less likely to give summaries, which you can sort of expect based on verbal ability. Now we're going to look at what happens in immediately preceding message, immediately preceding notes. It turns out opinions, as we said earlier, is much more likely to lead to a new idea. So an informal idea is more likely to lead to a more formal idea. It turns out that any of the types of characteristics we saw earlier tends to lead to asking explanation. Likewise, asking about use leads to asking for explanation. And elaborations or asking explanations lead to explanations. Again, any type of these messages will lead to summary. We can also go backwards in time. We look at 2 notes ago, what happened? Asking for explanation leads more because of explanations, usually during the intervening period. Also, asking about how something is used, giving an opinion, especially offering a different opinion, is much more likely to lead to explanation. The bolded part of the different opinion shows it's a very strong effect. Likewise, new ideas lead to summaries, but not immediately, 2 turns later. And going back further in time, we look at what happened 3 messages ago. After someone asks about how to use something, it tends to be a new idea 3 messages down the road. Also, giving examples tend to lead to further explanation. That will lead to explanations. Any questions on the layout of the results? So you can see a very complex model of what's happening. You have characteristics at the individual level on the far outside, and you look at what happens in the preceding turns of talk, or in this case, preceding messages. So we can see that you have results at different levels. You have individual effects, you have recent message effects. New ideas, request for explanations, and summaries. We see specifically that in terms of individual characteristics, gender and skill affect our online behaviors. And also, the notes aren't simply a list of messages. They create a micro-context that then affects the likelihood of subsequent notes. So one thing that comes out very clearly is that informal cognition tends to lead to formal cognition later. Initially, when people express their ideas, they're typically not very well formed. They are vague opinions, and they get formalized over discussion. Social cognition has strongest effects. Questions lead to new ideas, and different opinions tend to lead to explanations. So the different opinions you can achieve because once you have different views, you want to have some way of synthesizing those views, explanations, very important part of that. So there's several implications for researchers. First, the importance of grade points. In a standard conversation, we don't really think about differences of knowledge messages very clearly. Some are much more important than others. And so if you don't model these critical moments, these break points, you can lose a lot of what's going on. And they're not very easy to identify, typically, so it has been done previously. So this is a big move in terms of identifying how the nature of conversation or online discussion changes. We want to be able to model effects across people, across nodes, across groups, across classrooms, and a multi-level analysis come out with our as well as students. Once we have this complex model, we can tell you in a specific situation, this is what's likely to happen by combining these different events. We also look at sequences. Most of the work in online discussions focuses on individual actions, individual messages. And it makes sense that sequences are probably going to be work. It's not simply what you do, it's what you do in the context where people have done it. And there's a new method for statistical online discussions. There are also implications for teachers. So, as before, not every moment is the same. You want to be aware of particular moments that really radically change the entire lesson. The sequences are important. Don't just look at what one person says. Look what that person says in the context of what people said beforehand. And so, in the long term, we're going to create a tool that will analyze online discussions. We can't have teachers looking at hundreds of messages. There just isn't enough time to do it, especially if you have massively open online courses. We can have thousands of messages each week for each course. So once we model what's going on, we use our computer program that classifies each term, talk, or each message. And we use that to identify particular messages or sequences that are problematic. Then the teacher, instead of having to read through everything, they get a small set of like, these are really important conversations or online discussions people have had. Look at what's going on here and intervene appropriately. Something that isn't in this study but in other studies I've done is connecting these sequences to outcomes. So we want to know this particular sequence, if they engage the sequence more often, they tend to have better problem-solving outcomes. They tend to write better essays. They create better computer programs. So one way of doing that is by looking at the likelihood of sequence, does that affect the outcome? A more subtle version is, so the first one is at the group level, the outcome level. The second one is at the term level. And this is useful when you have not so many groups for lots of terms, for lots of messages. And here, we use the group outcome as explanatory variable. The interaction with group outcome has affected likelihood of subsequent interaction. So both these ways can be used to see if sequences are related to outcomes. So next steps. Right now I have lots of different computer programs that do these different things. So the important next step is to put them together in one coherent program. It's easy for, say, teachers to use. Then we need to test to see how well teachers use the programs, to assess how their students are doing and instrument properly. And then to refine the program over time. Because inevitably the first version probably has to be the greatest version. So then beyond this particular type of study, I'm also working with many people in different fields. And even though the method is called Statistical Discourse analysis, it actually asks a much more general question that it tries to answer, which is, what major momentary events affect people's behavior over time? During classroom conversation, which is the initial focus of my work, I've now moved on to online discussions. It also applies to one person's individual thinking, individual problem solving, as we do in Talk Aloud. We can look at things that take place in much longer periods of time. How does it influence learning a word? We can look at what that child's done over days, weeks, months. We can also examine something much more complicated. For instance, passing during basketball games. We can look at what people are doing with decision making how successful they are, both in terms of scoring a basket or winning the game. We can also look at stock market transactions. What affects the movement of prices over time? People's trades. And I'm working with someone to look at what affects the likelihood of war in Macedonia. So there's a whole series of events where it wasn't clear exactly whether they were typical war or not. And those things affect each other and affect the country over time. Thank you.